Welcome back, students. Today we're going to be doing factoring polynomials and working with expressions. Okay, so let's go ahead and start with polynomials and common factors. Okay, and I'm going to start off as an example. So when you're asked to find or to factor a polynomial, we're going to be assuming that you're looking at the polynomials with integers, right? If the polynomial, for example, does not have integers, then it is a prime, or we call it an irreducible over the integers polynomial, right? For example, x squared minus 3 is irreducible over integers, right? And we label integers as a letter z, right, in mathematics. That's how we label it. Meanwhile, z is the integers, and z is essentially a subset. So z are specifically integers, but we are working with real numbers in general, right? So real numbers are going to be capital R. Okay, so this is real numbers. This is integers. Okay, but how would we reduce x squared minus 3? We can factor it out over irrational numbers, right? And what would be that? So if we think about it, so x squared minus 3. So what number squared will give us 3? It's going to be square root of 3. So we can say x minus square root of 3 times x plus square root of 3. Right, but that is an irrational number. So a polynomial is completely factored when each of its factors is prime. So for example, we have completely factored. Going to be example 1, example 2. So if we have x cubed minus x squared plus 4x minus 4, right, we essentially can factor it in the following way. So it's x minus 1 times x squared plus 4, right? So neither of x minus 1 or x squared plus 4 are reducible, right? We are not reducible. So that means it is completely factored. Okay, now let's take a look at something that is not completely factored, right? It's going to be similar. So example 3. It's going to be, let's say, x cubed minus x squared minus 4x plus 4, right? And what is going to be? It's going to be x minus 1 times x squared minus 4. Right now the question, is it completely factored? No, it's not, because x squared minus 4 can still be factored. And now let's take a look what the final answer would be. So we still have x minus 1, but x squared minus 4 can be factored as x minus 2 times x plus 2. Now it's completely factored, right? So the simplest type of factoring involves a polynomial that can be written as the product, right, of binomial and another polynomial. So as an example, right, an example would be a times x plus a times y. So the common factor here is a, so we're going to have a times x plus y. Okay, so let's take a look at a few examples. So example number 4, we're going to have 6x cubed minus 4x. Right, so what is the common factor? The common factor between 6x cubed and 4x is actually 2x. Right, so we can factor it out. We can factor it out as 2x times 3x squared minus 2x times 2. And we're going to have 2x times 3x squared minus 2. Okay, so our factor here was 2x. Okay, let's say that this is example A. So example B. For example, we can have negative 4x squared plus 12x minus 16. Okay, so what can we do here? we can notice that we can factor out a constant. And what constant would it be? It would be -4. So essentially we can have -4 as a constant. So if we take it out of the equation, -4 times, so we're going to have x squared minus 3x, right? The sign has changed because if we bring it back, -4 times 3x, we're going to get 12x. And then plus 4. Right, so -4 is our factor. Okay. Perfect. Now, let me go ahead and give you the factoring special polynomials. So if we take a look at this table right here, we have some formulas that you can memorize by heart, and they are very useful, especially for algebra. So, here is factored form, difference of two squares. So when we have u squared minus v squared, we can always factor it out as u plus v times u minus v. A perfect square, it's a trinomial. When we have u squared plus 2 times uv plus v squared is the same thing as u plus v squared, in parentheses. And same thing, this difference. So u squared minus 2uv plus v squared is u minus v. Right, and we can prove it by rewriting it as u plus v times u plus v and applying the distribution rules we learned last lesson, and u minus v times u minus v. And we also have sum or difference of two cubes. So here, if you have the cubes, those are more rare to use, but still good to remember how we can factor them out. And here are a few examples. 9x minus 4. So what's square root of 9? That's 3. So we're going to have 3x squared minus 2 squared. So we can factor out as 3x plus 2 times 3x minus 2. Similarly for this one, x squared plus 6x plus 9 is going to be x squared plus 2 times 3 times x plus 3 cubed, which is the same thing as x plus 3 squared. Okay, similarly for the second one, and then for the last one, we can use the cube formula. Right, the cube formula, the sum of the cubes and the difference of the cubes. Okay, perfect. So, one of the methods that we can use to factor out squares, right? Because sometimes, even though person square is very nice, but not always is doable. So if we have an equation, right? We're gonna say second order factoring. One of the common ways we can factor is called cross method. So let's say we're given an equation, right? An equation of ax squared plus bx plus c, right? And we want to factor it out. So depending on the coefficients, right, we can factor out specifically b of x, right? And let's say for simplicity, we're going to say case 1 is a equal to 1. Then we have x squared plus bx plus c. Okay, so the cross method is involving the cross. And if we say that our numbers, our factors, let's say x1 and x2, right, if we add them together, we will end up with b. Right, and specifically, here it's going to be b. And if we are multiplying them, right, this is multiplication sign. Or actually, I'm gonna write it as a little star. Right, if we're multiplying it, then we're gonna get c. Okay, so we always think of what kind of numbers can it possibly be in order for us to factor out. Okay. And let's see. We can possibly do one example here. So I'm going to give you an example. So let's say x squared plus 3x plus 1. Right, and I'm going to use the cross method. So have b is equal to 3, c is equal to 1. So that means something plus something is equal to 3, something times something. And actually, let's say that it's not 1, let's make it at 2. right? Something times something is equal to 2. Okay, so what combinations of numbers can we have? It can be 1 and 3, or 3 and 1, 2 and 1, and 1 and. So 3 is not a, because if we have 3 plus 1, that's 4, so we cannot have it. But if we say, okay, we're going to say 1 and 2. We can do 2 and 1, it doesn't matter. But the reason why for a equal to 1, why it's nice is because, well, we can immediately say the following. Right, we can say x plus 1 times x plus 2. Okay, so we're going to have x times x squared plus x times 2. 2x, 1 plus x. 1 times x is x, and 1 times 2 is 2. So that's indeed squared plus 3x plus 2. Right, so the cross method works. So in case of a is not being equal to 1, case 2. So a is not equal to 0 or 1. Right, we have ax squared plus bx plus c. So our cross method is reduces to the following. So it's going to be b and then a times c. So we still have x1 and x2, right? And we have addition, we have multiplication. Okay, but now this example is a little bit more trickier, right? So let's go ahead and have an example here. So this was example here. Going to be 2x squared plus, let's see, wait, which was the previous? Okay, yes. 2x squared plus 5x plus 2. Right, for example. So then we have our b is 5. B is equal to 5. And our c is equal to 2 times 2. 2 times 2, which is equal to ac. 8 times c is actually equal to 2 times 2. Right? 8 times c is equal to 4. So we have that b is equal to 5, 8 times c is equal to 4. Okay, so we have something times something is equal to 4, and something plus something is equal to 5. So we're going to have 4 and 1, or 1 and 4. Right, but we're going to say, in this case, we're going to say 4 and 1. And okay, so how do we actually use that? And this is the most important part about factorization, is, say 4 and 1, is the following. So we're going to have 2x squared, plus we're going to break down the 5x into the 4x plus 1x, and then plus 2. Right, now, if we take a closer look, we can group it. We can group 2x squared and 4x and 1x and 2. Right, and so what are we going to have? If we factor out, what's the common factor here? The common factor here is 2x. So we're going to have 2x times x plus 2 plus, so what's the common factor here? It's just 1, so it's 1 times x plus 2. Okay, so between those two equations, what is the common factor? And the common factor here is indeed x plus 2. So the final answer would be x plus 2 times 2x plus 1. Okay, so now we are able to factor out any square polynomials by using the cross method. But there are a few more ways we can actually factor. And one of the ways that we can do it by grouping, right? Essentially, this application here was the grouping, right? Because I grouped them with the parentheses. So sometimes a lot of polynomials, once you rearrange it in order, right, from the highest power to lowest power, you're able to actually group them, and that was the grouping method essentially. Right, most of the time you can see it immediately. So the easiest way to think and to remember the rules is as following. So if we have a polynomial, right? If we have a polynomial, we can do the following. we can first factor out any common factors using the distributive law. Right, the distributive law is from the last lesson. Step 2, we're going to factor according to one of the special polynomials form, right, if we can. If we cannot, we're going to skip that step 2, right, because we can have that it's not a special form, it might be a prime, or it might be that we would have to use a cross method for. Okay, and then we can factor it by using a x squared plus b x plus c, which is the cross method, or we can factor it by grouping. Right, most of the time grouping works well on polynomials of a higher order, like a cube or a fourth power. Oftentimes it helps out to actually factor out nicer. All right, perfect. Now, let's go ahead and move on to the rational expressions. So, the second part of today's class is about rational expressions. And we touched on rational expressions last time in the previous lesson, but essentially here we want to talk about the domains of functions. Right, so what is a domain? Domain of a function, right? So we can have a function, and we call function f of x, right? Which means function of the x variable. Okay, so domain itself means that what values x is taking for a function to be valid mathematically. Okay? So, for the domain, it's only for the x values, right? If we have an f of x. So, and it's the number line, right? It's the number line of x. And let's see, let's go ahead and make a drawing. So, if we have the x-axis, and here we have 0, 1, 2, etc., infinity, positive infinity, -1, -2, negative infinity. So this axis, we call it x-axis, and this is our domain, right? And this is our domain for most of the functions, but sometimes the domain is restricted, and the rational functions are the ones which give a restriction. For example, we will have, if we take a look at this example, 2x cubed plus 3x plus 4. So the question, are there any numbers that violate anything? And the answer is no, right? So the domain is actually from negative infinity to positive infinity, right? There's two parentheses, that's our domain. So that means we would say that x belongs. So this symbol right here means that it belongs. Belongs to. So x belongs to negative infinity to positive infinity. Okay. How about the following though? What if we have something that might violate it? As an example of f of x is equal to square root of x minus 2. Right? This is a square root. When does a square root violate the rules? It violates the rules when we're trying to take the square root of a negative number. So that means x minus 2 must be greater or equal to 0. So what would be the x? So here we have an inequality. We haven't yet touched on inequalities, but this sign means greater or equal. Greater or equal. Right, the bottom line is the half of the equality, and the greater sign means that the left side is greater or equal to the right side. Okay, so if we solve for x, we would add 2 to both sides, and we would have that, so -2 plus 2 is 0, so it's x greater or equal to 2. Okay, so what if x is less than 2, we would violate the rules. So our domain, in this case, our domain is from 2 to positive infinity. Okay, perfect. And then the last thing The last example for the domain is, of course, for the rational expression. So a rational expression is a fraction. So let's say x plus 2 over x minus 3. So we have a numerator and denominator, which we covered last time. Right, but now we have to think. Remember the rules which we learned last time. We know that we cannot divide by 0. So that means that x minus 3 cannot be equal to 0, ever. Right, so let's solve. When does x minus 3 is actually equal to 0? Let's solve for it. So we can go ahead and add 3 to both sides. And we're going to get that x is equal to 3. So that implies that x can never be 3. Okay, this is very important, right? So how would we write a domain? The domain is going to be equal to, so we know we can be from negative infinity to 3, right? And then we would go from 3 to positive infinity. 3 to positive infinity. Okay, so but how would we say that this is a whole interval? We would have to put a union sign. So a union sign, it's this. This is called a union. So what we're doing, we're uniting the two intervals. Even though the 3 is not included and we can never be at 3, the interval is still united. So we know that this is the whole domain of our f of x. And I'm going to call it g of x. Right? F doesn't have to be always f. We can change on any variable. Most commonly in mathematics and in algebra, we f of x, g of x, or h of x. The most common one. Unless we have more functions, then we would have to come up with different lettering. Okay, so let's take a look at one more example. So if we have if we have 4x plus 12 over x squared minus 3x, right, we want to simplify. So how do we do that? How do we do that? So essentially, we'd have to factor out. So in the numerator, we can factor out 4. So we're going to have x plus 3. Okay, how about denominator? In the denominator, we can actually use the cross method, right? The cross method, and we have that something plus something is negative 3, something times something is negative 18. So what would we have? Something plus something. So we're going to have negative 3, so that means we can have 3 and negative 6. Right, that would satisfy the equation. So, okay, that means we will have x minus 6 times x plus 3. Notice, we have x plus 3 and x plus 3 in numerator and denominator. So what can we do? We can cancel them out. Okay, so we're going to end up with 4 over x minus 6. And that would be our answer. Okay. Perfect. For example, we can also have complex fractions. I mentioned it previously, but we haven't solved any examples on it. So for today, for the last example of today, let's go ahead and solve a complex fraction. So we would have 2 over x minus 3 divided by 1 minus 1 over x minus 1. So the first step is to actually bring it to the same denominator in both numerator and denominator. So we would have 2x minus, so how can we have the same denominator? Let's go ahead and multiply by x and divide by x. So we're going to have 3 times x over x. Okay, and then we're going to divide by, so 1 minus 1 over x minus 1. How can we bring it to the same denominator? So we're going to have x minus 1 over x 1. Okay, minus 1 over x minus 1. Okay, so what are we going to have? We're going to have 2 minus 3x over x divided by x minus 1 over x 1. Now let's actually simplify. Can we simplify numerator? I don't think so. How about denominator? Yes, we can. So 2 minus 3x over x divided by, so we have x minus 2 over x minus 1. Okay, and then remember the rules that we learned last time. So when we're working with a over b divided by c over d, it's the same thing as a over b times d over c. Okay, so we can rewrite this as 2 minus 3x over x times x minus 1 over x minus 2. And let's go ahead and multiply. So we will have that 2 minus 3x times x 1 divided by x times x 2. Okay, so there are two things about the x. Even though in the beginning, it's important to notice that x minus 1, x cannot be equal to 1 and it cannot be equal to 0. Even though at the very end, if x is equal to 1, it seems like we are okay because the expression would be 0, but in reality we wouldn't be. So here, x is not equal to 0 or 1. All right. Thank you, guys. And for the next lesson, we're going to enter the linear equations and the rectangular systems of rectangular coordinate systems and modeling with linear equations. Thank you and see you next lesson.